Okay, so one small thing that we missed out on in the regression part was a parsimonious equation. So what a parsimonious equation meant was that after you have conducted all the steps in the regression analysis, uh, so basically you need to check for four things, which is that your R square is, at the acceptable limit, that there is a goodness of fit of the regression line, and the acceptable limit is 65%, but preferred is 70% and above. So that is one check post. Second is that you have the least number of independent variables possible in that equation. So you have to keep on eliminating your independent variables until you reach this parsimonious solution. The third checkpoint will be that all independent variables that are part of your regression equation have this, one sec. They are, sorry about that, they are all significant. So their significance value should be less than that of uh, the alpha value that you have. So if your alpha value is 0.05, then the significant value in that column of regression reading should be less than 0.05. And if you check all these three, then you will arrive at your most parsimonious or the best regression line or the best regression equation. So in continuation of regression, we'll move on to the next technique, which is factor analysis. So factor analysis, as per what we've been taught, is something that we use to increase granularity in your research. So basically, if you are talking about a particular independent variable, we need to figure out what are all the dependent variables which affect that independent variable in a regression. But there are so many, let's say, independent variables, and you can't make head or tail out of, you need to have some sort of idea ki, okay, these many variables uh, can be made into one particular variable or a factor. Then you use factor analysis. So what I'm trying to say is basically factors are groups of variables, nothing else. So factors are also called latent variables, mainly because they are not actual variables on which you are collecting data. So if let's say I take age, income, gender, class, whatever, seven variables like this, and I have collected data on each of these uh, variables, and then I want to club them and make a factor out of them called demographics. So then demographic will be a factor consisting of these individual variables, but demographic is not something that I will collect data on. That is why it's a latent variable. So all factors are called latent variables in that sense. And also, let's say you have a bunch of variables laid out in front of you, and you are saying yourself that okay, I am clubbing these five variables together, and I'm going to call them x, an x factor, and I'm clubbing the other few variables together. I'm going to call them y factor before running a factor analysis. This is called a priori grouping. So why a priori? A priori basically means something that you're doing prior to your analysis. So this is a prerequisite knowledge. So suppose you're a student and you're being uh, understood in the factor of like roll number, marks code, registration ID, all these things, and you're wanting to club factors into, or you're wanting to club these variables into two factors, let's say faculty-driven factors and student-driven factors. Just an example. Then these are your priori groupings, a priori groupings. And when you run factor analysis, it might so happen that your a priori factors or a priori groups may not remain intact, because factor analysis will help you understand which are the variables who are highly correlated, and you will then be able to group those highly correlated variables into one factor and remove, like, basically make it a dissimilar group as compared to other factors. So it will group all the similar variables together. All right. And so yeah, that's the basic funda of factor analysis, and there's a step as to how we go about it. Let me just check if I'm missing out on something. Oh yeah, so what AD used to say a lot is that basically when you are given a particular subject to analyze, and factor analysis will help you understand the underlying dimensions on which people are thinking about that particular concept. So if you are talking about a vague concept like brand equity, and you're measuring variables on the basis of a lot of things like purchase, your likeness of the color, likeness of the texture, a lot of, you have 40 variables, let's say, then you can use factor analysis to group those 40 variables into 5, 6 factors. And then you can present to your boss that, okay, so these are the dimensions along which a customer analyzes brand equity for a particular brand. So that's what factor analysis is used for. Also, one more thing that factor analysis can be used for is as a prerequisite step of regression, where, let's say, like, if you remember, I told in the last video that there should be no auto correlation. There should not be a high correlation between the independent variables in the regression equation. So what happens if you do have highly correlated independent variables? Let's say y equals to x1 plus x2 plus x3, and x1 and x2 are highly correlated. We cannot use that in the regression equation. So what we will do is we'll club x1 and x2 variables in one factor and call it A. And that factor will have a score, or a factor score, which we will be using to run the regression. Then that becomes y equals to A plus x3. And A and x3 are not correlated, so we can run that regression analysis. So factor analysis can also help in reducing the multicollinearity problem or the non-auto correlation problem that someone might face while doing a regression analysis. Yeah, so here we can go over the deck, and I think this will only be explained in very simple thing. Yeah, so corporate reputation, let's say, if you want to measure what corporate reputation means to people, you can do factor analysis and find out on what factors or what dimensions people are thinking about corporate reputation of a company. Yeah. So the whole point of factor is to reduce the number of variables that you're dealing with. So you're trying to club things into similar groups. And there can be two kinds of factor analysis: exploratory and confirmatory. So exploratory and confirmatory both, like, you can use basically, while doing exploratory research, you can figure out how many factors you want, and then to confirm, you can run the factor analysis saying that, okay, make give me a 3 factor solution or give me a 4 factor solution, and find out if they are making sense or not. So yeah, this is something that we're going to look at. So there are 3 kinds of variances in within a factor: unique, common, and error variance. And all 3 of them make up the total variance. And there are 2 methods of doing it, among which principal component analysis is what we have done in class, as far as I can remember. So this considers the total variance of the factors, so of the variables, basically, which includes all the common, unique, and error variances. But common factor analysis only considers only the common variance, assuming that both unique and error variance are not being taken into account. So yeah, the use case is also given if it comes in the question. You can write: used when data reduction is primary concern, and this is used when you have to understand the underlying dimensions. So yeah, this is pretty much an algorithmic process now. What happens is you have to capture the data in terms of an interval scale. An interval scale is a metric scale. So when we ask them the Likert scale or the staple scale when we use, if you can remember, we have learned in RN. And also you can go back to Naresh Malhotra and figure, like, to see it pictorially, it might help better. It's all there in the book, very nicely mentioned. So when you are collecting data on an interval scale, you are basically uh, collecting data on a metric scale, which you can measure. So 1 to 7, 1 to 5, something like that. And once you have captured that data, then you run it through SPSS. And in SPSS, you can do 3 things, where basically, firstly, an intercorrelation matrix will be made, where you will have all the variables plotted on one side and all the factors plotted on the other side. And based on the matrix and figuring out the correlation, we'll get into the details of this as we go on. So yeah, so firstly you will get an initial solution which will have all the correlation between each factor and each variable in that intercorrelation matrix. And on the basis of that, you will make a second table, which is called a component matrix. And in the component matrix, what you will get is a factor loading. And how they will be put to use, will come to it. And basically, using factor loadings, you will have to conduct this process called rotation of a vector. So even I am not clear as to how rotation of a vector actually happens, but what it does is it basically increases the disparity between highly collinear variables and very less collinear variables. So variables which are very highly correlated, their factor loadings will increase, and the ones which are not correlated, they'll decrease a lot. So if say one is 5.5 and the other one is 4.8, by rotating the variables, 5.5 might become 7 and 4.8 might become 2. So now it's easier for you to understand which variable is correlating more with which factor. Yeah. So, all right, cool. So I think we can go in one by one. So principal components method is here's what's going to happen. You basically have, let's say, a plot like this where x and y axis you have respondents scattered randomly throughout the entire plot. And what basically will happen is using that OLS method or using certain algorithms within the SPSS system, factor analysis technique will run lines through it, which will be like each line will be a factor. So factor one, factor two, factor three, like this. And these are all vectors basically. So vectors, as you know, will have both magnitude and direction. And using these vectors, you'll figure out that whichever, like let's say a respondent, which is this data, this particular variable is closer to factor 1 or closer to factor 3. So if you were to impose this factor 1, 2, 3, 4, these lines on this plot, you would figure out that graphically, whichever factor this particular respondent is coming close to, that factor will have a high correlation or a higher factor loading. This variable have a higher factor loading onto factor 3, let's say. And when you rotate the factors, when you rotate the vectors, you'll figure out whether actually factor 3 is where this particular variable will go or not. If it's still confusing, we can go into the output of what is happening. So this is the component matrix. So component matrix is what's happening is these are all the variables plotted here. Okay, so 1, 2, 3, 4, 5, 6. So 6 variables are there. And these are the probable factors that we give 1, 2, 3, 4, 5, 6. So 6 factors are there and 6 variables. So now you can see which, let's say this correlation that is mentioned over here, 0.609, is the factor loading of attribute 1 is basically the variable, this particular variable on this particular factor. Now you will have to figure out, just give me a moment. Yeah. So you will have to, using the factor loadings, you will understand which variable is more highly correlated towards which factor. So as you can see, this attribute 1 is clearly more highly correlated to 1 and 2 as compared to 3, 4, um, yeah, 3, 4, 5, and 6. So these factor loadings will help you in analyzing whether this particular variable will go into factor 1 or 2 or 3 or 4. So still factor 1 and 2, they still have very close values, 0.609 and 0.608. And the disparity between whether this particular variable will go into factor 1 or 2 will be made sure using the rotation of the vector. So let's say maybe if it is loading more onto factor 1, then this value might become 0.80 something, and this value might become 0.5 or 0.40. Then that will mean that attribute 1 is loading more onto factor 1, and attribute 1 will become a part of factor 1 in that case. Now the concept of eigenvalue comes. So eigenvalue is an index of the strength of the factor, and by the strength, it said that the amount of variance that it accounts for. So what basically eigenvalue is calculated is how it is calculated is that if you take all these values, not all of them, sorry, let's say 6.609, 0.614, 0.593, 0.728, 0.6767, and 0.764, and you square all of these and add them up, then you will get the eigenvalue of factor 1. Then similarly, these values, if you square and sum them up, you will get an eigenvalue of factor 2, so on and so forth. So which of these factors you will actually include in your uh, which of these factors you will actually extract out of this analysis will depend on this eigenvalue. So the yeah, it's mentioned here. It's 0.61 square plus 0.61 square plus, there should be an addition sign here, plus 0.959 square. So like this, you are adding up all the factor loadings of that particular factor to get this ultimate eigenvalue. And as a checkpoint, you have to take only those factors, you have to extract only those factors which have an eigenvalue greater than 1. And so let's say over in this solution, there are two factors which have eigenvalue greater than 1. And let's say the first attribute itself is explaining 46.7% of the variance in that all the variables over there. So as you can see, the more you add factors into your analysis, into your design, the more factors you extract, the more and more your variance in your data will be explained. And how you're getting to that is the cumulative percentage. So cumulative percentage is nothing but addition of these numbers. So as you can see, the first component only has 46.7. So cumulative is 46.7. But when you are adding another factor into it, that factor itself is addressing 27% more variance. And this cumulative percentage will take into account both of these. So both 46.7 plus 27 will give you on as a total variance that you can explain is 74.334%. Now, where should you stop is also another checkpoint over here, that if you are getting explaining more than 70% of the variance in the data is something that you can go forward with. Ideally, when you keep on adding all the components, all the factors, you will explain 100% of the variance, but you cannot do that because you need to, once again, like regression, you need to achieve that parsimonious solution with the least amount of data, with the least amount of, not data, sorry, the least amount of variables. How much can you whether you can get to an acceptable range of explainability of variance or not. So if 74% of your data is being explained, of the variance in your data is being explained by only two factors, and both of those factors have a higher eigenvalue than 1, then you can go ahead with these two factors. And how, yeah, so all the thumb rules will be written over here. Right, correct. So yeah, as you can see, eigenvalue is greater than 1. And so then you basically uh, load all your variables onto these first two factors. So this is your exploratory design, get it? So exploratory design mein you are say checking all the components and figuring out ki हाँ ठीक है, so my all my variance will get explained by including 6 factors in the process. But if I want to run only 2 factor solutions till the second component, now I will go and do a confirmatory research where I will ask SPSS to give me a 2 factor solution, and then I will get to see all the factor loadings. Then I won't get to see all these 3, 4, 5, 6. I'll only get 1 and 2 factors, and then I will get all the factor loadings of each variable on factor 1 and factor 2. And upon rotating those variables, I will find out, let's say variable 1, variable 2, and variable 3 are loading onto factor 1, and variable 4, 5, and 6 will load onto factor 2, depending on the rotated data, the rotated vectors. So I will get which variable belongs to which factor, and that's how my factor analysis will be completed. Once again, it's not true that suppose you are going ahead with a priori grouping that these are the variables which I will group as this factor. These are the variables I will group as that factor. It might not happen. Like if you think intuitively that variable 1, 2, 3 will be factor 1 and variable 4, 5, 6 will be factor 2, it might not happen. So any of these variables 1, 5, 6 might become factor 2, the other rest can become factor 1. But it's clearly it's imperative that each variable will be part of only one factor. And once you get the factors, there will be an option to calculate a factor score, and those factor scores will be loaded onto your SPSS data view. And what will you do with those factor scores is that you can run, let's say, a regression if required. Instead of using the variables that you have, you will use the factor scores of the new factors that you have arrived at. And that will take care of your non-collinearity, the multicollinearity effect that you are trying to avoid. So yeah, so as a summary, all you have to do is design the questionnaire, collect the data, clean data, run factor analysis. Okay, this is the clean data and everything you have to do for all the techniques. And I think sir spoke about that while teaching cluster analysis. So we'll talk about that then. Look at
Bro, एक question था.
yeah, Aryan, yeah, go ahead.
Yeah, could you please repeat a factor scores? How are we calculating factor scores?
Yeah, just give me a second. So factor scores are basically uh, a weighted measure of the responses. So let's say you have the variable values, right? So each of these variables, let's say Q, W1, R, Q1, will have a value
Yes,
for each respondent, and you
right.
will multiply that with the factor loading of this attribute. So factor loading of this is
Understood.
0.609, let's say. You will multiply that with the variable data, and you will sum all the data. Get it?
Got it.
So if there are three variables, let's say these three variables are part of one factor, you will multiply the factor
Right,
loading of this into the data that you have collected of the respondent of this variable,
right.
and you will add all of them. So summation of factor loading into variable score, a variable data. Okay,
Got it.
that's how you
Got
calculate the factor score. And also one more
it.
thing is KMO statistic, which it's a fact of the, I think he had said that it has to be greater than 0.6. I'm not too sure as to the conceptual level of what a KMO statistic actually does or how you have to calculate it. But it's a checkpoint if it's asked in the question. As long as I think you mentioned that KMO statistic should be greater than 0.6, you should be able to score. So yeah, that's about factor analysis. Uh, we'll move ahead with conjoint.